Welcome to an overview of core concepts in machine learning, where we'll connect big ideas to practical tools. The slide shows a neural network, a layered processing diagram, and a grid to hint at different data shapes. And over the next slides, I'll summarize how these pieces fit together and why they matter for building real models. Machine learning mainly follows three paradigms. Supervised learning maps inputs to known labels when you have annotated data. Unsupervised learning uncovers hidden structure or clusters from unlabeled inputs, and reinforcement learning trains an agent to optimize sequential decisions through trial, reward, and interaction with an environment. So choosing the right paradigm shapes your data and evaluation strategy. At the foundation, we have regression methods. Linear regression predicts continuous values, and logistic regression estimates probabilistic class boundaries, both by minimizing differentiable loss functions. To handle nonlinearity or mixed data, we extend beyond regression with decision trees, random forests, and SVMs, which let us model complex feature spaces and high-dimensional patterns. Feed-forward neural networks stack weighted linear maps and nonlinear activations in a one-way flow, and we train them with backpropagation and gradient descent to minimize error. These networks are universal approximators that enable complex mappings, but practical training needs careful initialization, regularization to avoid overfitting, and hyperparameter tuning to reach stable performance. When we want to discover groups or simplify structure, clustering and dimensionality reduction help. K-means partitions data into compact spherical clusters. Hierarchical clustering builds nested groupings without a preset K, and PCA linearly projects high dimensional data into lower dimensions while preserving variance to speed downstream tasks and aid visualization. Autoencoders learn compressed representations by encoding inputs into a bottleneck and reconstructing them, which is useful for anomaly detection and denoising, while self-supervised training leverages large unlabeled corpora to learn contextual embeddings that transfer across NLP, vision, and speech domains, enabling powerful features without manual labels. A core modeling challenge is balancing underfitting and overfitting, described by the bias-variance trade-off. Too simple models miss signal, too complex ones memorize noise, and the validation curve helps find optimal complexity. Practical solutions include using validation curves to guide choices and ensemble methods to reduce overall error by mixing models. Evaluating models means more than accuracy. For classification, we must handle class imbalance and look at precision, recall, F1, and ROCall to understand trade-offs, while for regression, we quantify error with MAE and MSE, and report R-squared or explained variance, so stakeholders can judge how much of the signal the model captures and what error to expect. Finally, small models and AutoML accelerate efficient innovation by enabling near-Rs SOTA performance on edge devices with lower compute, and by automating feature engineering, architecture search, and hyperparameter tuning to democratize ML, reduce time to MUCAD, and make responsible, scalable deployment more achievable.